All right, welcome to today's class. It's October 20th. This is Math 55, and it's the fall 2022 version of the course. So today we're going to talk about how algebraic expressions involving binomial coefficients, the n choose k terms that we talked about in the last couple of classes, actually reveal interesting information about how to count different objects. So we're going to focus on looking at what are called combinatorial identities. These are equalities that happen with binomial coefficients and tell us more than meets the eye. So let's look first at the binomial theorem to remember what it is. This is something we talked about classes ago, and see how manipulating the binomial theorem can give us these expressions. So recall that the binomial theorem states that if n is a positive integer, then if you take the binomial x plus y and raise it to the exponent n, the expansion has a predictable form. I want to remind ourselves what this is all about so we'll be able to understand the stuff that we do afterward. So here you have the binomial x plus y multiplied n times. So when you actually do the multiplication, expanding, you'll be picking from each one of these binomials one of the terms. So I might pick the x here, another x in the next one, maybe a y from this one. And in total, since you have n binomials, each term will have a total degree of n. You might have k x's that you chose from each of the binomials in total. And if you do, you have n minus k y's you must have chosen for a total of n terms. Now, what we discussed last time is you can actually predict the coefficient, and that coefficient is n choose k. So x plus y raised to the n is n choose k times x to the k, y to the n minus k. And k here, the number of copies of x you select, can range between 0, selecting no x's, and n, selecting an x from every single one of these. Okay, so let's play around with this, manipulating it and maybe plugging in values. So let's look at what happens when you plug in x equals 1 and y equals 1. So on the left side, you'll get 1 plus 1 to the n. On the right side, you'll get the sum of these binomial coefficients with 1 plugged in here. So here, these will become just 1. And so you're left with 2 to the n plus the sum, or equals the sum of the binomial coefficients. So does this reveal something about counting? Well, let's interpret each side and see if they actually count the same thing in two different ways, which then gives us this combinatorial interpretation of what this equality might mean. We know that this object here counts the number of k element subsets of an n element set. It's n choose k. So we'll start by interpreting this piece and then interpreting the entire sum to be able to understand why these two would be equal altogether. So the kth summand of the right side counts the number, that's short form for number, the pound sign, of k element subsets of an n element set. So I'll pick a particular n element set of the set 1, 2, up to n. All right, and now we're summing over all possible values of k, going from 0 to n. So we're counting the 0 element subsets, 1 element subsets, etc., all the way up to the n element subsets. That covers all possible sizes of subsets. Any subset of the set 1 through n has size between 0 and n inclusive. Inclusive means that we include the possibility of 0 and n. So the right side counts the total number of subsets of the set 1 through n. And it does so by counting the 0 element subsets, 1 element subsets, etc., up to the n element subsets. Okay, so this entire right-hand side actually counts the total number of subsets of the set 1 through n. So if it's the case that this counts that as well, then these would be equal. So we should figure out why this side, the left-hand side, actually counts this same thing. So the left-hand side, 2 to the n, must count the same thing, but why? Well, we actually proved this on one assignment, but I want to talk about the solution. The form that this number takes on is one number to the exponent of another one. So you would think that there might be a way to do this by thinking about Cartesian products, which we talked about at the beginning of the combinatoric section of this course. And we can do that. There is a one-to-one correspondence between subsets of the set 1 through n and elements of the set 0, 1 raised to the n. Now, I want to remind ourselves what that actually means. So here we have a set. We're raising it to the n. What we mean by that is we're taking the Cartesian product of n copies of the set itself. So this is altogether n tuples of points whose coordinates are all in the set 0, 1. Now, what is this correspondence? This correspondence sends a subset S to a particular element in this n-fold Cartesian product, where A sub I records whether or not I is actually in the set S. So A sub I equals 1 if I is in S, and is 0 if I is not in S. So let's look at a concrete example of one of these so we know what this correspondence is looking like. So for example, if n was equal to 5, then the set S equal to 1, 3, 4 would be mapped to the 5 tuple 1, 0, 1, 1, 0. It's telling us that we have a 1, a 3, and a 4. And we see that this is a one-to-one correspondence. This tells you exactly the elements that belong to the set, indicated by the things that are actually 1. So the number of subsets of the set 1 through n is the size of this n-fold Cartesian product and this is the size of the set. We are taking a product of n times raised to the n, which is 2 to the n. So we do have that the number of subsets of an n-element set is 2 to the n, which then gives us this equality that we wanted to establish through a counting argument showing that both sides count the same thing, the number of subsets of the set 1 through n, in two different ways. And that's going to be the theme of what we do today, thinking about how to count things in these two different ways. So let's look at our next example. All right, so the next thing we're going to think about is this problem right over here. Given positive integers n and k, with k less than n, explain why k times n choose k is equal to n times n minus 1 choose k minus 1. Now we could expand all of this algebraically and maybe come up with a conclusion, but the idea is to interpret how these two things are counting the same phenomenon, but just in different ways. So we'll start with this left side because we have the binomial coefficient n choose k, which we have a straightforward application of, which is selecting, or interpretation of, which is selecting k elements from an n element set. Now the question is how to interpret this additional k here. So n choose k, we select k elements from an n element set. I want to think about this in terms of things that we're actually familiar with. Like, let's think of this as choosing k students from a class of n students. What would this additional factor of k do? It would be like distinguishing, after you've selected your group of k students from the class of n students, one particular student. Maybe we can think of that student as being the leader of the group of k students you selected. Okay, so we can think of k times n choose k as counting the number of ways to choose k students from a class of n students and selecting one of these k students to be a leader. Okay, why? This is because there are n choose k ways to select k students from n students, and for any such selection, there are k choices of leader. Okay, so the process we employ to get this number, k times n choose k, is selecting k students from a group of n and then selecting a leader. Now, this is supposed to equal some other count. And so we think of the question of how can we do this process in a completely different way? Well, the process involved two things, selecting the group of students and then selecting a leader. We could have instead select the leader first and then select the remaining students to fill the group of k students overall. A reason why it might be reasonable to think that this is an approach that would give us something near this is because if we select the leader first, we actually select the leader from the entire class of n students, and so we'll get n possible ways of doing this. Okay, so let's see how the rest of this transpires if we use that interpretation to count. So how can we perform the above procedure in a different way, we could have instead selected a leader for a group. There are n ways to do this. Because there are n students. Total. Now, for any such selection, what do? We need to fill up the rest of the class, or the rest of the group, right? So we must select, if the group size is k, and we already selected the leader, we have to select k minus 1 students of the remaining n minus 1 to form the rest of the group of k. So we're selecting k minus 1 students of the remaining n minus 1. There are n minus 1 choose k minus 1 ways to do this. For a total then of n ways to select a leader, and for every single leader selected, n minus 1 choose k minus 1 ways to choose the rest of the group. And that is exactly the quantity that we wanted on the previous page. Great. Okay, so this again gives us this staple idea that we're counting something in two different ways to establish this equality, and this equality has hidden in it information about counting. So we'll do one more example that's slightly more complicated than the ones that we had above. Let's try this one. Prove that for any positive integer n, 1 times n choose 1 plus 2 times n choose 2 plus 3 times n choose 3, etc. up to n times n choose n is actually equal to n times 2 to the n minus 1. Now, in each of these situations, the left and the right-hand side, it's actually not clear what either side can be interpreted as. But sometimes it is advantageous to start with the side that looks algebraically the simplest because it may have an easier interpretation. Right? So the right-hand side looks like we're picking something that has n choices, and then we're selecting a subset of a set of size n minus 1. So this here is the number of subsets of an n minus 1 element set. And so since we have n things here, it might be the case that what we're doing is selecting one of n things and then selecting a subset of the rest. Okay. So we'll do this in terms of interpreting in terms of physical objects. We'll say we have a group of people. So suppose we have a group of n people. And we'll do the following process. We will form a committee kind of using the idea we had in the previous problem, selecting one of the n elements in the set we'll think of as picking a leader. So form a committee by selecting one person to be a leader. And we know how many ways there are to do this. There are n ways to do this. And then selecting any subset of the remaining n-1 people to be members. Okay. Any subset. There are 2 to the n-1, because that's the number of subsets of n-1 people, ways to select the rest of the committee independent of the leader chosen. It doesn't matter what leader you choose, you'll have that many ways to select the rest of the people. Okay, so there are n times 2 to the n-1 many committees that can be formed this way. Okay, so what we've done here is we've selected a committee by first selecting a leader and then subsequently selecting all of the other members. Now, a natural thing to do is, why not do this in the opposite direction? Pick the committee first and then select a leader. Now, because of the way that we did this, you always have to have a leader, so the committee size will always have size 1, at least 1. Right, so now how do we interpret the left-hand side? Well, any particular summand seems like, if you look at any one of these summands, it seems like you're picking a certain number of students and choose k for some value k. And then of the k, you're selecting one of those k. That's like selecting one of those k to be the leader. Okay, so we'll go ahead and do that and see if it matches up with that interpretation of the other side. Right, so again, we have a process here that's 2 steps. Right, we've interpreted this right-hand side as a process involving 2 things: selecting a leader and then selecting the rest of the committee. And so doing that in reverse will likely give us this other side, which gives us the combinatorial reason for the algebraic interpretation. So instead of selecting a leader first, select the committee and then select a leader. Okay. The number of ways to select a committee of a particular fixed size k is n choose k, and then independent of such a selected committee, it doesn't matter which type of committee you choose of this kind, there are k choices for a leader. Okay, so this gives a total of k times n choose k ways to complete the process for committees of size k. Now the committee sizes have to go from 1 to n because they're forced to have a leader. Committee sizes range from 1 to n, not 0, because a leader must be chosen. Okay, so the total number of ways to perform the process is going to be the sum of all of these things. This takes care of ones with committee size 1, then committee size 2, up to committee size n. And there you have it. So I think the overall story behind these is that you have some type of algebraic expression that might be true, but might be hard to establish for a lot of different reasons, like this one. Actually proving this algebraically might be difficult. However, you can prove this by actually interpreting what's happening on either side combinatorially. And the way to do this is pick a side that you feel more natural with. For example, here we said we thought we had a more natural way of deciding how to count the right-hand side. And then that count, because there's a product here, had two processes involved. Selecting something involving the n and then selecting something involving the 2 to the n minus 1. If we switch the order in which we do this, it might reveal what's happening on the left-hand side. Okay, so I do want to end with one observation, which is you can actually prove this particular identity algebraically. It's just a little tricky to do. So I'll write this as an aside. You notice that things in this expression kind of look binomial theorem-like you have all of the n choose k's appearing. But we'll do something that is a little bit of a twist from that. So we know that x plus 1 raised to the n is equal to n choose 0 plus n choose 1x plus n choose 2x squared all the way up to n choose n x to the n. So we've used the binomial theorem here, where we've set y equal to 1. So y is the term that is right over here, usually in the binomial theorem, and then we get powers of y as a consequence inside of these things. Now, depending on how we actually did this, we might have written the exponents in the reverse order, but luckily these binomial coefficients are reflective, meaning n choose k is the same as n choose n minus k. Okay, so the next step is somehow to introduce something that would encapsulate this here. Now, when we plugged in x equals 1, we got 2 to the n, and we kind of want to n 2 to the n minus 1. So the idea of getting an n something n minus 1 looks kind of like using a derivative. So we'll differentiate both sides of this. If we differentiate on the left side, we will get n x plus 1 to the n minus 1. And then the right side, we'll get n choose 1. And then the constant n choose 0 disappears. You get n choose 1, then 2n choose 2, 3n choose, so apologies, you get 2n choose 2x. Then the next term here will be n choose 3x cubed. So you get 3n choose 3x squared. And this continues until you have n choose n x to the n minus 1. Okay, now if we substitute x equals 1 in this expression, we end up with n times 2 to the n minus 1 on the left side. On the right side, we get n choose 1 times 1 plus 2 times n choose 2 plus 3 times n choose 3, all the way up to n times n choose n. So we do end up with the expression that was given in this problem, but you see that the process of actually going through this algebraically is not one that's straightforward whatsoever. It's not clear to take something like this and actually differentiate to get the expression you want. But using this stuff that we built, we're able to sometimes interpret these things combinatorially. Okay, so I'll suggest trying this one. Try to figure out a way to figure out this equality. I'm going to leave this blank because you have an assignment problem that's actually related to this expression. Okay, as a hint, try to interpret what this side is, and then see how you can interpret this as counting something different by looking at what the expression on the left is trying to explain. Okay, so that's about it for our combinatorial identities, which are these really interesting phenomena of seeing algebraic expressions like this or like this that have hidden inside of them combinatorial meaning.